Okay. Okay. We discussed on brace cut design. Okay. Actually, it is slightly related to the lateral earth pressure. Okay. However, there are some modification has been made, okay, by Terzaghi, okay, which is not similar with the lateral earth pressure calculation. Okay, because it is actually based on the observation that has been made by Terzaghi on sandy and also clayey soil. Okay, so the same procedure where he has used the distribution diagram, okay, to estimate what will be the lateral earth pressure acting on the sheeting pile, for example. Okay. Okay. So deep excavation with vertical side require lateral support to prevent cave in of the earth and to protect the adjacent areas against ground subsidence and lateral movement of the soil. Okay. So when excavation are shallow and ample space is available, okay, the side of the excavation can be sloped at a safe angle to ensure stability. Okay. However, in deep excavation, especially in built-up area, there may not be adequate space for providing safe slope. Moreover, it becomes uneconomical to provide safe slope because of large quantity of earth involved. Okay. So that is the problem related to the very where the site is very limited area. Okay, so it's not very practical to have a slope. Okay, in order to have a deep excavation. Okay, so in that case, okay, the use of the bracing system, okay, is could overcome this to prevent actually from the site to collapse. Okay. So this is an example of the bracing system. Okay, so where they have a sheeting system to protect from this, sorry, to protect from the soil to collapse. Okay, and this bracing system used to support, okay, from this sheeting to give support from this sheeting side, okay, to protect from the soil to collapse. Okay. So excavation which are laterally supported are braced. Okay. The vertical side of the excavation are supported by a sheeting and a bracing system. Okay. It consists of a relatively flexible sheeting placed against excavation wall. The lateral thrust on the sheeting is resisted by the horizontal member in compression. They call as a strut. So bracing is provided as the excavation proceeds and face of the sheeting become exposed. So various type of bracing system is adopted to make the excavation stable. Sheet piling is used primarily as the bulk kit to hold or restrict the lateral movement behind it. Okay. So this is example of the bracing system. Okay. So it may first, sorry. Okay, first they need to install the sheeting system. Okay. either the common one is the sheet piling. Okay. So after they install this sheet piling to act as a wall, okay. So then they start to excavate, okay. So this will be the first step, and then the next step, okay, is to install the bracing system, okay. So when we look on for the whole system, okay, so this is the sheeting, okay. So then they will put a wheel, they call a wheel, okay. So a wheel will be have the same direction with the sheeting system, okay. So then there will be a strut, sorry, okay. So then we put the strut, okay. Then they continue for the to to dig until it reach the required height or depth. Okay, so this is the example of the third step until it continue to the required height that they want to achieve. Okay, so a gravity retaining wall is a permanent structure used when an excavation is permanent. But when excavation is temporary, excavation for building or subway, the excavation is filled with a structure which then permanently retains surrounding soil or earth. Okay. If the temporary excavation is made in sand, the wall of the excavation must be supported during construction of the building by a system of bracing. Okay. So actually the bracing is a temporary structure. Okay, so after they has construct, they do the excavation. Okay, then they will construct a permanent structure. Okay, then they will remove this bracing system. Okay, laying underground pipeline, construction of bridge abutment, construction of basement, metro railway construction of subway tunnel is among the example is among the example construction that require for the bracing system. Okay, so or if we use the trenchless system, okay, so it's not required for us to have this kind of bracing. For example, construct for a tunnel, okay, so no need to have a bracing. But when we want to construct for the terminal of the subway, so we need to have we need to use the bracing, or we can use another system, which is we call as a tie-back system. Okay? But we will not discuss on the example for the tie-back. I will just introduce what is the tie-back system. Okay. So then we have four types of a common brace cut system: vertical timber sheeting, steel sheet pile, soldier beams, and tiebacks. Okay. So this is a vertical timber sheeting. In this method, vertical timber sheeting consisting of the plank about 8 to 10 centimeter thick are driven around the boundary of the proposed excavation to a depth below the base of the excavations. Okay. So they use a plank, a wood plank. Okay. The soil between the sheeting is excavated. The sheeting in is held in place by a system of wheel and strut. Okay, so this is the wheel. So the wheel is have a same alignment with the timber sheeting or the plank. Okay, so the strut have a certain should be arranged at a certain spacing. For example, 4 meters for every spacing. The wheel are the horizontal beam running parallel to the excavation wall. The wheel are supported by the horizontal strut, which extend from the side of the excavation. Okay, so A is example of the use of the wheel and strut, while B is another example where we want to have a little bit, we want to extend, or we want to have a very uh, a width, a large width. Okay? So they use a rakers, but still use the wheel. Okay, and for every spacing, they will apply the raker system. However, need to make sure that the bottom layer of soil, okay, is very firm, okay, in order to make sure it's stable to install the raker system. However, if the excavation are relatively wide, it's become economical to support the wheel by inclined strut known as rakers. For inclined strut to be successful, it is essential that the soil in the base of the excavation is strong enough to provide adequate reaction. If the soil can temporarily support itself, an excavation on limited depth without external support, the timber sheeting can be installed in the open or in a partially completed excavation. Okay, normally vertical timber sheeting are economical up to a depth of 4 to 6 meters. So that is for the vertical timber sheeting. So we have another for the second approach is the steel sheet pile. Okay, pile or sheeting driven in the close contact to form a continuous interlocking wall which resists the lateral pressure of water or earth. Okay, in this method, the steel sheet pile is driven around the boundary of the proposed excavation. A continuous line of pile is driven in advance of excavation as the soil is excavated from the enclosure, wheels and strut are placed. Okay. So the wheels are made of the steel. The lateral thrust from the side is resisted by horizontal member called strut and placed across the excavation, and wheels and which again the wheels, the strut may be of the steel or woods. Okay, so I guess the same approach with the timber sheet system. As the excavation progresses, another set of wheel and strut is inserted. Okay, so this is the step. The process is continued till the excavation is complete. It is recommended that sheet pile should be driven several meters below the bottom of excavation to prevent local heaves. If the width of the deep excavation is large, inclined bracing may be used. Same with the timber type, which is they call as a rakers. The upper strut is placed where the excavation is shallow and the little laterally of soil has occurred to change appreciably the original state of the stress. As excavation proceeds downward, the lower part of the face is freely to yield inward before it could be restrained by the next strut. The inward yield of the soil increase with the increase of the depth of excavation. This problem is analogous to a retaining wall tilting about it tips, the sheeting tips about it tops. Okay. So this is just an further explanation on the soil behavior. Okay. So to overcome the lateral yield, so that's why they include the next strut. Okay. So this is the sheet steel pile. Okay. So this is the sheet pile. For one example, so they will have a continuous sheet pile with a wheel Okay. And the example is given here as well. Okay. So this is the sheet pile, and this is the wheel, and this is the strut. Okay, from the plan view. Okay. So this is from elevation view, where we have a wheel, strut, and sheet pile. So on the calculation, we need to determine what will be the sheet pile properties, wheels, and also the strut. Okay. Then the other one is the soldier beam, okay, where they use the H pile, okay, which are driven at suitable spacing of 1.2 to 2.5 meter around the boundary of the proposed excavation. Okay. As the excavation proceeds, horizontal timber plank called legging are placed between the soldier beams. Okay. So they install the H beam. So the H beam will have a spacing 1.5 to 2.5. So the between of the H beam, they include the what we call as the legging, okay, to protect for the lateral movement of the soil. Okay. So when excavation advanced to suitable depth, width, and strut are inserted, the legging is properly wedged between the pile flange or behind the back flange. Okay. So uh, so this is the elevation and the plan view of the soldier beam methods. Okay. So the last one is the tie back. Okay, in this method, no bracing in the form of strut or inclined rackets is provided. Therefore, there is no hindrance to the construction activity to be carried out inside the excavation area. The tieback is a rod or cable connected to the sheeting or legging on one side and anchored into the rock, into the soil or rock outside of the excavation area. Inclined holes are drilled into the soil or rock, and tensile reinforcement is then inserted and the hole is concreted. So then they include the reinforcement system, they call a tendon. Okay, then they apply the tension force, okay, to make sure that the soil and to make sure that the sheeting system, okay, connected well with the tendon system, and also to ensure that it can stabilize the the soil. And then last of that is usually formed at the end of the hole. Each tieback is generally pre-stressed, okay, before the depth of excavation is increased, further to cope with the increased tension. Okay. So the advantage that we have that the contractor have as a full space, okay, without having uh, uh, a bracing system that could uh, could have a difficult during the construction stage. Okay. So lateral earth pressure,
I think,
column.
yes, yes, doctor, I think pre-stress system like that.
Yes. Precise.
Yes.
So they will apply a pre-stress. Okay. So Rankine and column earth pressure theory cannot be used for the computations of the lateral earth pressure on sheeting, as those theory applicable to rigid retaining wall rotating about the base. Okay, so that's why Terzaghi come up with his own approach, okay, for this brace cut system. Okay, the sheeting and bracing system is somewhat flexible, and rotation takes place at the top of the wall. Okay, so sheeting are placed against the wall of the excavation when these are shallow. Okay, the upper strut is placed when the excavation is shallow and the lateral yield of the soil has occurred. As the excavation proceeds downward, the lower part of the face is free, yield inward before the next strut is placed. Okay. So the inward yield of the soil increase with an increase in the depth of excavation. Thus, the sheeting tilts about its tops. So the method of earth pressure of calculation has been developed by Terzaghi based on the observation of the load in strut in full-scale excavation in sand in Berlin and in soft clay in Chicago. Okay, so then Terzaghi has developed the earth pressure for the bracing system based on the observation for both type of soil, which is sand and soft clay. Okay. Pressure distributions, again, the sheeting have been approximated on the assumption that each strut support the sheeting area. The effect of the various factor is not fully understood. However, the result of the field study can be used as a basis for developing a pressure diagram required for the design of the bracing system. Okay, so it means that the Terzaghi has come up with the solution based on the full scale observation. Okay, and although there are some effect that is not fully understood. Okay. The pressure diagram recommended for design represent an envelope which encompasses the actual pressure distribution diagram obtained from the field test. These design pressure diagram are also known as apparent pressure diagram. Okay, so this is the apparent pressure diagram. Okay, has been uh, uh, discussed in detail by Peck in 1969 after Terzaghi. Okay, so the uniform distribution for brace cut in dry or moist sand, okay, where the pressure diagram is uniform with pressure equal to 1.6 times PA over H, or can use the KA value, which is 0.65 times unit weight times H times KA, where the KA is the tangent square times 45 minus 5 over 2. Okay. Where PA is the total normal active pressure on the wall, height is determined by the column theory. Okay. So the resultant active earth pressure diagram is 28% greater than the column active pressure for dense sand and 44% greater than for loose sand. Okay. So since the sheeting cannot resist, in general, the vertical shear force and the friction and addition of them are assumed to be zero. So this assumption has been made. Okay. Okay. So we have three types of apparent pressure diagram. Okay. The first one is for sand, okay, and for clay. Okay, we need to check for the stability number. Okay, where if the value is less than 4, so we may consider it is a firm clay, and the apparent pressure diagram is similar like the B. Okay, and if greater than 4, so we may assume it is a soft to medium clay. Okay, and the diagram is similar C. Okay. So the formula are given here, okay, to determine what is the PA, okay, for every type of conditions. Okay. So for example, for sand 0.65 unit weight times H times Ka. Okay. So for the firm clay, K times unit weight times H, where the key coefficient of K is 0.2 to 0.4. Okay. And the last one for the soft to medium clay, the maximum value of the PA is unit weight times H minus 4C. C is the cohesion value. Okay, so we look on one example. Okay, and this example is related to a dense sand. Okay, so means that we may use the apparent pressure diagram for A, okay, to determine the value or the properties for the pile wall section, wheels or strut. Okay. So a long trench is excavated in medium dense sand for the foundation of a multi-story building. Okay. The side of the trench are supported with sheet pile wall fixed in place by strut and wheel as shown in figure 20.17. Okay, so this is the example. The soil properties are unit width 18.5. Okay, C is equal to 0 and P is equal to 38. Okay. So we need to solve the problem for the A to D, okay, where the first one, the pressure distribution of the wall with respect to the depth. Okay. So for this situation, we may use the apparent distribution diagram of a sand. Okay. So the solution for A, for a brace cut in sand, use the apparent pressure envelope given, okay, which is in B, okay, figure 20, which is this one. Okay. So the equation for PA is equal to 0.65 times unit weight times H times KE. So the value for the unit weight is 18.5 and the KA, okay, could be determined based on the tangent square times 45 minus 38 over 2. So then the value for the PE is equal to 23. Okay. So that is for the solution for A. Okay. Then we need to count for the strut load. Okay, the strut are placed horizontally at a distance of 4 meter center to center. Okay. So it means that for every 4 meter, there will be another strut system. Okay. Okay. So to solve the problem, the reaction of the end of strut A, B, and C are represented by RA, RB, and RC respectively. Okay. For reaction RA takes moment about B. Okay. So since the location is symmetry between AB and BC, okay, so we can just solve the problems, okay, by using the moment concept, okay, to get the value for the RA and also RB. Okay, so this is the shear force diagram, not related to this one. Okay, the shear force diagram will be used on the C example. So okay, draw a simple moment diagram. So here we have a the load. Okay, this is the, yeah, from here we can draw the moment diagram. 23. Okay. So, and then this is will be the R B. They call it RB1 because this will be another for RB2. Okay. Then we have here RA. Okay. So RA times 3, okay, where our datum is RB1. So the distance is 3. Okay. So RA times 3 equal to 23, okay, times 4, and then times 4/2. Okay. So that will be for the to get the value of the RA. Okay. So 23 times 4 and then times 4/2, okay, which is equivalent to the moment for the distribution pressure of 23 4/2. Okay. So then later on the RA is equal to 61.33. Okay. So to get the RB, okay, so we need to have an equal value between the value from the 23 times 4, okay, which is equal to RA times RB. Okay. So the RB1 is equal to 30.67. Okay. So due to the symmetry of the load distribution, RB1 is equal to RB2 and RA is equal to RC. Okay. Now the strut load R L is equal to 4. The distance is 4. Okay. So then for every 1 meter value 61.33 should multiply with 4. Okay. So then it will become 245 kilometer for the PA. Okay, and for the PB is equal to RB1 plus RB2, which is 61.34 times 4 is equal to 245 as well. And the last one is the PC is equal to 245 because it is similar with the PA. Okay. So that is for the strut load. Okay. So what should we do next? Okay. Next, we need to look on the catalog. Okay. What will be the capacity that could be sustained by the strut members, okay, which is up to 245 compressive load. Okay. So then moment of the pile wall section, to determine moment pile at different point, it is necessary to draw a diagram showing the shear force distribution. Okay. So considering section DB1, B2E of the wall, okay, in figure here, this one, okay. Distribution of the shear force are shown in 20.17 C along with the point of the zero shear. So the moment at different point, okay, may be determined as follow. Okay. So for example, to get the maximum moment, to get the moment for A, okay, okay, MA, what's okay, MA, okay, MC, okay. So we need to get the area for this distribution, sorry, shear force diagram. Okay, so that will be represent for the MA. Okay, half time 1 time 23. So similar with the MC, which is this one. Okay. Okay, while for the MM, okay, so the MM, this one, okay, which is the half time 1.33 times 30.67. Okay. And for the MN, also same, which is half time 1.23 times 30.67. Okay, so that then the maximum moment M max is equal to 20.4. So we use the maximum value. Okay. A suitable section of sheet pile can be determined as per standard practice. So the next is to look on the what we call on the catalog from the supplier. Okay. So what will be the value for the M max for the sheet pile? Okay. So you need to know how to draw the shear force diagram from this moment diagram. So the last one is the maximum moment for wheel. Okay, the bending moment equation for wheel, okay, is equal to R L square over 8. Okay, so 245 times the spacing of strut, which is 4 power by 2, divided with 8. So the value is equal to 480. So a suitable section for the wheel can be determined as per standard practice. Okay, so the same with the wheel, the same with the sheet pile and also the strut. So we need to look on the catalog, okay, to identify which one is what is the suitable um, material to be used. Okay. So that is for the bracing system, brace cut system. Okay. So I also include one example. Let me open first. Okay. Uh, for the case of what we call as clay, okay, for the firm clay. Okay. So this is an example, okay, for the firm clay. Okay. The base example is shown above. Okay, determine the earth pressure envelope, strut load at ABC, section model of sheet pile, section model of the wheel at B. Okay. Strut are placed 3 meters center to center. So this is the property value, okay, of the clay. So for the clay example, the first step is to determine the stability number. Okay. So in this example, the stability number has been determined. Okay. So the value is less than 4. Okay. So means that the condition of the soil, okay, is considered as a stiff clay. So for the stiff clay, we should use this apparent distribution diagram. Okay. So the pressure will be C, therefore 0.3 times 18 times 7, which is equal to 37.8. Okay. So 0.2 to 0.4, so the average will become 0.3. Okay, so that is for the PA or sigma A value. Okay, so then to calculate for the strut, the same approach, okay, where we may use this the diagram, okay, the pressure envelope diagram. Okay. So get the moment, okay, because the location is symmetry. Okay, the location of this problem is symmetry between the A, B, and C. So means the A and C is symmetry. Okay. So we may use the same approach with the one that we have learned for the sand, where we introduce B1 and B2. Okay. And then get the same later on value for the PA and PC. Okay. So then for the section modulus of pile, okay, this is the reaction diagram, okay, or we call a moment diagram. So then we can get the shear force diagram. Okay. So from this example, we need to determine what is the distance between E and B1. Okay. Because later on we need to get the moment at E, okay, and also the moment at A, or the area of EB1 and also A area. Okay. So the X, okay, can be determined, okay, based on the this equation. Okay. But I also not familiar by using this equation. Normally we use a simple triangle law. Okay. Where for example, we know the distance between A to B, which is 2.5. Okay. So this EB will become X will become X. Okay. So 42.23 over 2.5 minus 1 minus X equal to 42.2 over X. So from there we can get the X value. Okay. So I guess because this is not very linear line, okay, so most probably 42. You just divide the 42, the maximum value 45.2 with the 37.8, okay, which is equal to 1.196. When I use the simple triangle law, so I get 1.2 something. Okay. Okay, so that is for the X. Okay, so the magnitude of moment at A, okay, which is equal to 3.6. Okay, and the value for the E is equal to 27.03. Okay, so then you can look again. Okay, so due to the symmetry, E is equal to C. Okay, so here's the maximum moment is 27.03. Okay, so therefore section modulus is equal to over the the uh, the the maximum value of the steel material, okay, which is 170 times 10 power by 3. So this is the section modulus calculation. Okay. So then for the section modulus of wheel, okay, by using the same with the example in the sand. Okay. So which is the P times S square over 8 So we obtain the value for the reaction. So from next calculation, we get the section modulus, which is the reaction over the compression of the steel material. Okay, so then we get the value for the section modulus for the wheel. Okay, so that is all for the base cut system. Okay, so I guess that's only for today. Okay, so we will meet tomorrow morning at 9. Okay, to have a lecture on the EC7. Okay, so that's all for our today class. Okay, so I will share all the recorded lecture in the e-learning by tomorrow. Okay, that's all. Okay. So Assalamualaikum and good afternoon.
Thank you, Dr.
Prof.